go. Give me a number between 10 and 20. Anyone?
11.
Excuse me?
11.
11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let this be x naught. And let's look at the entropy of the next symbol, A through Z and space, given the fact that I have a T here. Well, what follows a T? Vowels follow T, and H's follow T, and blah, 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 and spaces follow T. So, I might have an H of x1 given x0. But now what about the preceding symbol before T? I have an H of x minus 1 given x0. Well, symbols that precede T are vowels and so on, usually not an H. I know caught is C-A-U-G-H-T and so on, but so on. Basically, the process looks different going this way than that. I would expect an asymmetry. But look at this. And I'm not going to put that up because I'm going to use it in a minute. If I write h of x0, xn, two different ways, h of x0 plus h of xn given x0, and I write it also is equal to h of xn plus h of x0 given xn. So I've written a chain rule, expanding it AB and then BA. Now, because of stationarity, this is h of x0. The entropy is independent of n. And because of stationarity, I can subtract n from each of these indices because the joint distribution will be unchanged. X minus n, x0. Aha. These terms are equal. These sums are equal. Therefore, these are equal. So we conclude that the entropy n steps in the future, given the present, is equal to the entropy n steps in the past, given the present. That's what we prove very simply there. Well, that's nice, because the process is not time symmetric, but the unfolding of the uncertainty is. And now we see some of the mystery of the second law evaporates, because if you dip into a stationary process and you ask how the uncertainty unfolds as you go this way, it's the same as the uncertainty decreased coming in. These are equal. That means, say, a gambler going backwards in time will make the same amount of money as a gambler going forwards in time, say, gambling on what symbol comes next, or which horse wins the next race. So here's an example second law type of statement, right, says Hx and increase is refined to a conditional entropy, and then we find that the second law is built in to stationary processes. No physics needed. Okay, let's begin going through the talk here. And I'll turn off these lights. Okay, that's the talk. Okay, it's been noted that if you take a coffee cup and throw it on the ground, it breaks. And you seldom see a broken coffee cup coming up into your hand and making itself whole. When you see a movie, you can tell which direction time is going. The car crashes are sort of asymmetric in time. So we ask what's going on with the physics and the mathematics for these processes. All right, the first law of thermodynamics says that energy is conserved. Look, if I have a number of billiard balls on the table having elastic collisions, the total kinetic energy is unchanged because of the elastic collisions. The velocity, the positions, everything changes, but the total energy stays the same. This is conservation of energy. Now the second law has to do with energy too. It says that there's something lost in most physical processes. You lose energy. Well, yeah, I drop a ball, bounce, 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 bounce. It's lost. All that potential energy, all the kinetic energy is lying there. But aha, inside the ball, the atoms are vibrating. No energy has been lost. It's just been turned into what you might call heat. So the second law says, although energy increases, useful energy decreases. For example, if I have a hot water and cold water, I can run a steam engine. And then eventually it results in lukewarm water. I can get work out of that. I can take the energy out of that inhomogeneity and use it. I add up all the energy, it's still the same. But notice when I get warm water, I can't get any more energy out of it. Now, is that true? Well, yes and no. If I went in with tweezers the size of molecules, I would notice that some of the molecules were moving fast, you know, the Maxwell-Boltzmann distribution. Some were moving slow, and I could make a little engine the size of one molecule to extract that. But as you can see, it's hard to be satisfied with that. In other words, I really don't think you can get energy out of a homogeneous distribution, that is, out of warm water. Sure, people have looked at Maxwell's demon. He lets hot molecules through one way and cold through the other, but he's gaining information about the molecules, and so in the process of turning warm water into hot and cold so he can run a steam engine, he's interrogating the atoms, and in the process he's heating them, and you can argue that he's a cold demon, and when he comes into equilibrium with this process, as he's opening and closing the doors, letting hot molecules cold through, as he comes into equilibrium, then all of a sudden he's unable to affect the distribution. It's the chattering of his door. He's as hot as the molecules, and it's pretty persuasive that the demon cannot extract energy from it. But in the process, we come into contact with information theory, because there's the information that the demon is gathering to open and close the door, and you haven't reduced the system to the one before the demon got there until you've zeroed out the demon's memory. And Landauer, among others, has argued that every bit of memory that you delete, the demon increases the entropy of the house. Log. Well, let's just say, when you zero the memory, it costs you energy to do it. So you can equate information and energy. So let's get back to what we can get for free. So the second law says entropy increases, and there's some nice consequences of it. One is no perpetual motion. Things go towards equilibrium. And in black hole physics, it was thought that, there's a real problem. If you have a black hole, and you have a gas that has a lot of entropy, and you throw that gas into the black hole, now you've just increased the mass of the black hole and size of the event horizon. So you've destroyed entropy. Entropy decreases. If you throw elephants in and dictionaries in and so on, it makes no difference. So it seems two things are true. One is that information is lost in a black hole. That's not very nice. And the second is that the black hole violates the second law of thermodynamics. It says entropy increases because I can throw it away. But Bekenstein and Hawking noticed that the event horizon grows when you throw something in, and they argued that it grows just enough so that with the right multiplicative constant, the second law is preserved if you count the area of the event horizon as entropy. And then later that was taken seriously. They said, well, if it has entropy, it has a temperature. If it has temperature, it radiates, and you get Hawking radiation, and so on. In preserving the second law, you got some very nice conjectures about what's going on in physics, and they turned out to be true. And as I mentioned in a lecture a while ago, the entropy of a black hole, which is essentially the log of the number of ways you can create it, the number of distinguishable ways you can create it. The entropy of a black hole is 1 bit per square Planck. what the plank is.